How Agoda manages 1.8 trillion events per day on Kafka, from the Agoda Engineering and published on Medium. So I know these titles appear a little bit marketerial, but let's see the content. At Agoda, we send around 1.8 trillion, because I can have a loop that sends so many events with the same event. But let's read this. This should be hopefully good. At Agoda, we send around 1.8 trillion events per day to Apache Kafka. We first started using Kafka in 2015 to manage analytical data, feed data into our data lake, and enable near real-time monitoring and alerting solutions. So both operationals and actual data, they send through the Kafka. Over the years, Kafka usage at Agoda has grown tremendously, 2x growth year over year on average, reaching 1.8 trillion in 23. Now, more of our engineering teams are using Kafka in their applications. Our use cases for Kafka have broadened, and beyond serving an analytical data pipeline, it now functions as an asynchronous API, facilitating data replication across our on-premise data centers, and also playing crucial, so also business logic, actual replication of data, not just analytical or store in data lake. And also playing crucial role in feeding and serving data from our machine learning pipelines, but still data. With the scale and rapid Kafka usage, because some use cases can use it to actually do some business processes, but this is fully data. With the scale and rapid Kafka usage growth, particular challenges arose that had to be tackled. On this blog post, we'll attempt to outline our journey over the years and explain some of the key approaches we took for our ever-growing Kafka infrastructures. This is going to be interesting. What happens when your usage of Kafka is growing and growing and growing? How do you push the limits? What do they do? 1. Back to basics. Simplifying how developers send data to Kafka. In 2015, we decided to employ an architecture of logging data events and separately forwarding the data into Kafka. The idea was simple. A client library used by the development teams would write events to disk, and a separate daemon process called forwarder would read the events on the disk and forward to Kafka. This is a repeating pattern. This is a perfect pattern. You write things to disk, you forward to Kafka. The client library was responsible for a daemon process, an agent for them. The client library was responsible for handling file rotation, managing write file locations. The forwarder, on the other hand, was responsible for reading the files and retrieving the events, metadata, Kafka topic, the payload type, etc., sending the event to Kafka, tracking files offset of what was sent, managing the deletion of completed files. So we have the client library, which writes, so far this blog post looks promising because it is clear. I really like it. It's really clear so far. I'm going to subscribe to them because they are doing a good job so far. Client library writes to disk, then they have the forwarder, which writes to Kafka. Two-step logging architecture. The log to disk and then forward to Kafka. Let's call it two-step logging architecture. Served several benefits, the first of which is to separate operational concerns away from the dev teams. The lightweight forwarder would be deployed as a daemon service across every node in our infrastructure. Yeah, so sometimes this is a sidecar. Sidecar is an actual container in Kubernetes. Sometimes this is a different prod. Sometimes this is just an agent. I like the simplicity of just having another daemon, another process across every node in our infrastructure indirectly managed by the Kafka team. Kafka team could perform operational tasks such as dynamically configure the forwarder remotely to route events topics to a different Kafka cluster, or block it without impacting applications or requiring changes from the dev teams. Configure optimizations, example Kafka batching, compression, and linger settings without dev teams intervention. Roll out upgrades to forwarders independently of dev teams, example. We can roll out Kafka client fixes without needing to chase teams to upgrade lib dependencies? Yeah, so because this is agent, you don't need to compile the other applications, right? Because this is another process. When another process deploys, you don't need to compile your application. It's not a library. Upgrade Kafka without needing to chase a bulk of Kafka producers if Kafka client protocol change by upgrading the forwarder. So again, we have the client library which sends directly to disk, and then we have the forwarder which collects, and the forwarder is a process that is controlled by the Kafka Ops team, routes or blocks events based off remote config, remotely configures batching optimization, and upgrades transparently. Forwarder is forwarding to Kafka. Other benefits of the architecture also include simplified API for producers who send events without requiring any Kafka knowledge or dependency. Yeah, the client lib is just simple disk logger. Enforcing serialization standards by embedding serialization logic into our client libs. Example, our client libs can enforce Avro serialization for all events by working in tandem with the schema registry. So they have some schema registry. Let's see if they describe it. Writing to disks adds a layer of resiliency, for example, in case of connectivity or Kafka issues. Trade-offs taken. With our approach, the client library has a hard dependency on the forwarder process to send data to Kafka. Indeed, we do have here a dependency on a process. This means that the Kafka team has to ensure that every node in the Agoda has a forwarder process running healthily, and they are tasked with taking care of this deployment, upgrading, monitoring, and the SLAs. Although this results in a more complex architecture, the operational complexity can be easily mitigated with proper monitoring and automated tooling. At its core, the main trade-off is increased latency for better resiliency and flexibility. Our two-step logging architecture is only used for sending analytics data. Using our approach, we can achieve 99 percentile latency of 10 seconds measured and end-to-end from application client to writing to disk, folder, sending to Kafka, and data being ready for consumption. We think that 10-second latency is acceptable and sufficient for most analytics workloads. Depending on the topic, cluster, use case, we can further tune the forwarders to achieve lower latencies of 1 second at 99 percentile, utilizing smaller batches but lower overall throughput. What if we need a lower latency than 1 second? But what about critical and time-sensitive use cases that require sub-second latency, such as applications will still write to Kafka via Kafka client libs? Okay, so such applications will still write to Kafka. There is no such decoupling, the write to disk and then consume from disk. Write to Kafka via Kafka client libs from their application, bypassing the two-step logging architecture. We believe that this gives a nice balance of the simplicity of the two-step logging architecture for the bulk 85% of Agoda's developers. I like the balancing, how they choose different solutions for different requirements. So 85% of Agoda's developers who only want to pass on some analytical data to Kafka and do not have a sub-second latency requirements. Delays of up to 10 seconds is acceptable. The flexibility to produce to Kafka directly for specific but less common use cases requiring sub-second latency. Thinking about Kafka cluster layouts, multiple smaller Kafka clusters instead of one. Large Kafka cluster per data center. Early in our Kafka journey, we also decided to split our Kafka clusters based on the use cases instead of having a single Kafka cluster per data center. There were two main reasons for this. This is also a pattern that repeats. Some queues are split between slow and fast. When you have different needs, you split it, but note that they still have a single, a global Kafka cluster. It's not that each team, each app is responsible for its own Kafka cluster. To isolate any potential issues and their impact on the single Kafka cluster, flexibility to set up and configure clusters differently. In example, cluster would have different hardware specs and configurations depending on their use case. Okay, so they have priority Kafka, local Kafka, global aggregate Kafka, telemetry Kafka, which is better than just one Kafka to rule them all. Brilliant article, simple. I think they're laying it out really great. The person who writes this is really good. Smaller Kafka clusters based on use cases are easier to manage. This strategy and the two-step logging architecture explained in the previous section enables us to route Kafka events to a different Kafka cluster transparently, without any change from the producer applications via the forwarder. Though changes to any existing consumer teams would still be required, such routing changes do not occur often. The per-topic nature of such routing configs also usually means that only a handful of teams will be impacted by such changes. 2a. Don't cheap on Zookeepers. For Zookeeper, we provision dedicated physical nodes, no, not co-located with our Kafka nodes, using a dedicated SSD disk of Zookeeper logging and snapshot data directories, respectively. Given that Zookeeper is critical to healthy Kafka cluster operation, this setup was done to isolate the Kafka and Zookeeper nodes. We wanted to preemptively mitigate any potential issues between Kafka and Zookeeper, so they placed the Zookeeper on physical nodes that may arise down the line. This setup has worked well thus far. In the future, the plan is to migrate to a new Kafka version that removes the Zookeeper as a dependency entirely. 3. Building confidence, Kafka monitoring and auditing. Getting Kafka broker stats wasn't enough. We needed developers and stakeholders to trust that the data they consume is complete, reliable, accurate, and timely. With the Kafka layout and primary data delivery mechanism dealt with, the next thing we turned our attention was auditing and monitoring the Kafka pipeline. For monitoring, we gathered stat via JMX trans piped into Graphite as a backend time series data, store and visualize metrics using Grafana. However, we also understood that just getting the Kafka broker stats wasn't enough. We needed developers and stakeholders to trust that the data they consume is complete, reliably and accurately and timely. Inspired by Kafka 260, we went about adding Kafka auditing to our pipeline. A separate thread would run in the background on our client libs from two-step logging architecture asynchronously and aggregating messages counts across time and buckets. Kafka messages, Kafka topic A, timestamp, source host. Audit counts, they count it. Getting audit counts. So what do we have here? A client library writes to disk, forwarder, forwards to local Kafka. Cross DCs, they have a global Kafka, and then to data lake. And and they count, like, let's count after the local Kafka, after the global Kafka, after the data lake. And we see that after the global Kafka, the total count was reduced for time buckets from 0 to 5 to 90 from 100, so we know there was a problem there. So throughout the pipeline, we do some counting to make sure that all the counts are the same in different stages of the pipeline for some previous time buckets. These generated audits were then piped into a different Kafka cluster spawned solely to store audit information. Across our many Kafka clusters, we reuse the two-step logging architecture explained in the first section as the delivery mechanism by adding different Kafka endpoints for audit events. The audit info ultimately ends up in White Falcon, internal real-time analytics platform, and Hadoop, allowing the Kafka team to monitor and set up alerts on the pipeline health using Grafana and Superset. Having the data in White Falcon also made it much easier for the Kafka team to drill down and pinpoint problems whenever there were issues. And so they have some dashboards where they look at the data. At any point in time, we can be sure of how many events were sent across different pipeline stages, giving the Kafka team a high-level overview of the accuracy and latency Kafka pipeline. Together with our Kafka broker status, Graphite Grafana, the audits provided us with comprehensive view of the overall health for keeping out with growth, knowing when to scale Kafka clusters. Our next challenge was to figure out when any specific Kafka cluster required expansion. Example, adding more nodes naively, we started by using the percentage of the available disk as the key metric to determine if a cluster required expansion. We found out quickly that this was a bad idea since Kafka retention can be dynamically configured per topic. Disk usage capacity metrics did not accurately reflect Kafka cluster capacity. Since many factors contribute to the overall availability of capacity of Kafka cluster like CPU, network disk, and total partition count, in our second iteration we wanted a more holistic measure of a cluster capacity that took multiple resources metrics into account. Each of the resource metrics we wanted to measure would be compared against an upper limit, defined as the max limit we are comfortable with having the cluster run this. This would be recorded as the current resource metric upper limit represented as percentage. We would then take the maximum of all the percentages as the overall capacity of the cluster. This simplified capacity down to a single number. It signifies the dominant resource constraint on available capacity. Key capacity metrics we monitor in our Kafka cluster: disk usage per cluster, disk usage, storage used, network utilization, CPU utilization, total partitions per cluster, request handler average idle percentage. By setting alerts threshold based on the derived overall capacity percentages per cluster, the team can look into the capacity constraints and decide if there are issues that warrant for further investigations, or if it's time to expand the cluster physically. Subsequently, after adopting this way of calculating cluster capacity, we found that the capacity numbers are also useful when scaling down clusters. 5. Ensuring healthy data growth, attributing cost back to teams. As data continued to grow over the years, we reached a point about 1+ years back where we were starting to ask ourselves how much of the data being sent was needed. The perception was beginning to grow that the data platform, including Kafka pipelines and our data lake, turned into dumping ground. Much of the data being sent stored wasn't generating value. To tackle this situation, we took a page out from the playbook of cloud providers, put a monetary dollar value on usage, and attribute it back to the users. The core concept was simple. Have dev teams be responsible to what they use, in our case Kafka usage, and to manage and be accountable for the cost incurred. For Kafka, generating monetary value for teams' usage meant picking a suitable metric to measure and allocate cost against. For simplicity, we ended up picking bytes sent. We deliberately chose to ignore consumer usage as we didn't want to penalize team consuming data, since the whole point of the democratization of data was to allow people to use the data. Instead, we think that the onus is on teams producing data to justify storing it. Interesting. At Agoda, every Kafka topic has an owner team assigned as part of the topic creation process, making the entire cost attribution process much easier to implement. To determine the cost per byte, we took the total cost of our Kafka clusters together with the derived cluster capacity numbers from knowing when to scale Kafka cluster section above to extrapolate and estimated 100% capacity and what that would entail in terms of total bytes per day. From there, we can derive an estimation of cost per byte for use in our cost attribution models. When rolled out, we found the ability to attribute a monetary value to data sent by teams to be extremely powerful in incentivizing teams to evaluate what they need or do not need. Overall, it transformed teams' mindset about cost management and encouraged them to be proactive at managing their cost and be good stewards of company resources. Eventually, this evolved to become more significant Agoda-wide effort to attribute cost for any system back to any dev teams, but that is perhaps a block topic for another time. 6. Rite of passage, authentication ACLs. There comes a time with any evolving Kafka cluster in production that there will be a need to add Kafka authentication and ACLs, assuming you started without authentication and ACLs. At Agoda, when we first started our cluster, we were initially using solely for application telemetry data, and authentication ACLs on Kafka weren't required at that time. However, as our Kafka usage boomed over time, we become concerned about our inability to identify and deal with users abusing and negatively impacting Kafka cluster performance. To clarify our two-step logging architecture, see first section above provided us some safeguards since we could block the forwarder if there were a sudden flood of events. Still, as Kafka usage grew, there were more and more use cases where teams needed to connect to Kafka directly. Bypassing the forwarder, additionally, new requirements were emerging when we needed to restrict user access to certain topics. Thankfully, implementing authentication ACLs in Kafka is well documented. We gathered information in the documents combined with our company-specific requirements. We completed and released our Kafka authentication authorization system in 2021. The additional point is we added extra components for generating and assigning credentials to this authentication system and let teams self-service request Kafka credentials. We have users requesting credentials and using the servers and sending events to Kafka. With this authentication and authorization system, the Kafka team is now able to manage users, set expiring times for credentials, block and allow users to access. Okay, so they added security and authentication. Next, we are testing for certificate authentication and encrypting data over SSL. 7. Not forgetting operational scalability automated tooling. Lastly, I want to touch on the topic of automated tooling briefly. As we managed more and more Kafka clusters, we knew we needed better tools to aid us and ensure that the operational processes remain scalable. Currently in Agoda, we use a mix of open source Kafka tools like voice control, Kafka UI, some in-house built tools for binary deployments, broker config, propagation, Kafka broker rolling restarts, and UIs for managing ACLs. To name a few, I don't think we will ever stop being on the constant lookout for new and better tools to add to our arsenal, and it's part of the parcel of managing such a system at scale. Conclusion. So what's the deal? Apache Kafka is a highly scalable, robust piece of software that is, by and large, relatively easy to manage. We find that the main challenges at scale have less to do with Kafka software per se, but more around other aspects like separation of operational concerns away from dev teams, thinking about your Kafka cluster layout, example how clusters are segregated and how data is sent, knowing when to scale up down, knowing Kafka cluster, adding monitoring and auditing. So you see, it's not about whether Kafka can handle it or not. It's more about how you decide to manage Kafka, as well as giving dev teams visibility into their usage and cost, having safeguards to identify and isolate possible bad actors in the pipeline quickly. What's next? Improving on the forwarder. One criticism of our two-step logging architecture was at runtime, the client could not get an acknowledgement if Kafka had received the message because all the client did was write to disk. As of writing, we are revisiting the forwarder architecture with plans to incorporate an endpoint that will give the client lib response after Kafka has acknowledged the message. In conclusion, we've learned a lot about expanding our Kafka clusters over the years. Kafka journey will continually evolve as we support Agoda's ever-growing needs. This was, really good, right? This was a really good article. It was so well written, so well taught. In general, the architecture, it looks good. Deciding when to use what, to use multiple things at different scenarios. Looks good. Same, clear decisions. It really looks good. I'll follow them.